WAS welcomes Robert A. Simcoe of the Francis L. Friedman Professor of Physics, the director of MIT's Kavli Institute for Astrophysics and Space Research, to the Westport Astronomical Society's online science lecture series. Dr. Simcoe studies the formation of the earliest stars and galaxies by constructing custom-built spectrometers for major astronomical observatories. And what a list of observatories he's been at. Yikes. So Rob Simcoe is a native of Westborough, Massachusetts, where he first acquired an interest in astronomy and telescope making as a family hobby through trips to the Stellafane, like we have coming up. As an undergraduate, he participated in the development of the photometric camera for the Sloan Digital Sky Survey, after which he moved to Caltech for graduate school. While there, he collaborated with Mark Metzger on the construction of a prime focus camera for the 200-inch Hale telescope at Palomar Observatory, and completed a thesis on chemical enrichment of the intergalactic medium with Wal Sargent using the Keck telescopes. In 2003, he moved to MIT as a Pappalardo postdoctoral fellow to make use of the newly commissioned 6.5-meter Magellan telescopes and joined the MIT faculty in 2006. 3 years later, he installed the Fire Infrared Spectrometer at Magellan, which has played a key role in the exploration of cool stars in the nearby universe and the discovery and characterization of high redshift quasars and measurements of intergalactic matter in the first billion years after the Big Bang. His research group is now focused on the construction of a new hyperspectral imager for Magellan named Lamas, as well as the first dedicated telescope using indium gallium arsenide detectors for astronomical surveys of the transient infrared sky and preparations for scheduled observations with the upcoming James Webb Space Telescope. It says upcoming. This must have been written a while ago. In 2019, Dr. Simcoe was appointed director of the MIT Kavli Institute for Astrophysics and Space Research. Please welcome Dr. Simcoe.
Thank you so much for your inaudible applause. I appreciate it. I really appreciate the invitation to come here. It's a pleasure to get to meet those of you that I've seen so far and see those terrific photos that you shared. This is really great stuff. And it's still, I love going to Stellafane. I was there last year. Seems likely I'll go this year again. So it's nice to be among your peeps a bit. So, let me talk a little bit about where I've gone since the days when I was purely an amateur telescope maker and user, to talk about work that we've been doing with the James Webb Space Telescope and other future telescopes that are coming up. So first, let me share my screen, and then I will attempt to play here. All right, it looks like everything is up and running. So as was mentioned, my scientific interests are sort of twofold. One is in building fun toys and the biggest telescopes possible. Usually I have to motivate that. I don't think I have to motivate it to this crowd. I think I've got maybe a slide in on that, but I can skip right over that one because I think you guys are sold. But the other part of my scientific interest is really in studying the earliest objects in the universe. And for that, we use these large telescopes and increasingly are needing to move into infrared wavelengths instead of optical. And I'll explain why that is. And there's a pretty picture on the back of this that has nothing to do with my research, but was just one of the first images taken with JWST. So the things that I want to discuss about or talk about today is just a little bit of motivation. I know that this is an audience that's kind of predisposed to be interested in astronomy, but I just thought it'd be good to share a bit of why I think this is important and why I think using these new great observatories, it matters to society. Why is it important that we invest in this? And then I want to share a little bit about what it's like using JWST and some of the first experiences we had bringing up this new instrument and some of the first science that we obtained with it. And then I just want to talk a little bit about some sociological aspects having to do with how it was that my group was able to get data off of JWST 2 weeks after it was released for scientific use to the public. So there's a kind of interesting story there that ties to other projects that I work on. So just to zoom out and start from a very broad perspective, I think it's important to remember that origin stories are a big part of humanity. And for many, many, many thousands of years, humans have always looked up at the sky as a way of trying to understand what our origins are. And there's different stories that different civilizations have come up with to describe what the origins of the universe, what the origins of life, what the origins of humanity are associated with. Um, you'll notice that many of these things, these stories have to do with the stars, right? I mean, if you look in many of the sacred texts across different civilizations, it's almost always the case that the origin stories start with a description of where the heavens originated. What's kind of interesting now is that we're kind of reaching a stage now where we can think about our origin story using not the framework of religion necessarily, but a framework of science. And this is really the first time in the history of humanity that we've been able to construct something that is testable in this way. And we bring tools to bear that are quite powerful, but still can speak to the same kind of questions, the big questions that animate, human inquiry, right? This is some of the most important things that we do. And I would argue that in the same way that great art and great music and things like that are fundamental to who we are as humans, the inquiry to understand who we are and where we came from is a big part of this, the human enterprise. Now, as I said, physics is kind of, you can think about it now as a framework to build an evidence-based origin story for how we came to be. And there's different approaches to how you can do this, but the scientific method demands that we develop theories for how these things came to about, or how we came about, and then we test it. And the theory for how the universe came about and how the Milky Way and our planets and humans started, well, it's a very complex theory because the universe started after the Big Bang in a fairly simple framework, but has emerged into a universe that is quite complex in the present day. And we can only model it using computer simulations. And here's actually I'm going to play a movie that I hopefully will show fairly smoothly of how a galaxy like the Milky Way forms. And so this is a numerical simulation where you put in different ingredients, including matter of dark and normal varieties, gravity, things like the ideal gas law, how you heat up gas, how it cools. And then you just let the physics go and let it clock forward. And here you see that what looks like an expansion, and that comes from the fact that the universe is expanding after the Big Bang. I'll pause this briefly. Let's see what happens if oh, no, that's not what I wanted to do. Let me see if I can go backwards. Okay, I'll let this play again. I just wanted to explain what this circle was. That is basically describing what the gravitational radius of a galaxy is. And what you see is that there's, in the left panel, you're seeing a plot of the gas density. And in the right-hand panel, you're seeing a plot of the gas temperature. And the gravitational radius of the galaxy grows larger as it accretes more and more matter as this galaxy forms. But what you notice is that something that looks like a disk galaxy, like all those beautiful pictures that we looked at the beginning, that those of you have taken of actual galaxies in the real universe, they don't actually start to look like, the simulations produce things that look like disk galaxies, but it only happens kind of towards the end of the history of the universe. And the nice thing about a simulation is that I can take this little slider bar and I can just turn back time, right? And so if I go back, halfway to the Big Bang, you see something that looks sort of like a galaxy. It's centrally concentrated, but it doesn't look like a disk. And if you go back even further in time, it just looks like a giant mess, right? And what you're seeing are future galaxies, right? This whole frame is going to become one object. But what's interesting is it's a bunch of proto-galaxies and little objects, all of which are going to merge together over the course of time into what will become a galaxy that's about like the Milky Way. So just sliding it forward again. And so the point is there a way that we can, turn the clock backwards and forwards and test this model, which is physics-based but numerically realized, to understand what these galaxies looked like in their infancy? And this is really what the James Webb Space Telescope was designed to do. And just to give you a sense, the time, when I say galaxies in the early universe, which is what I'm interested in observing, we're looking at galaxies when the universe is about 5 to 10% of its present age. And so sliding the slider back, it would be when things looked about like this. So the things that we're talking about when I say a galaxy, it's like a pixel or two on this scale. And it's nothing like what you would think of as the Milky Way. And so I just want to keep that framework in mind as we go forward, that it's actually pretty amazing that we can use telescopes with today's technology to wind back the clock that far and look at these things that are just, they're like little embryos of things that will become future galaxies. Now, this is really only possible, and I always like to remind people of this, that it's kind of amazing that we actually live in a society that's willing to take some fraction of the public wealth and apply it to answering big questions in science, right? So the James Webb Space Telescope was a $10 billion effort. It was originally scoped a lot lower than that, but there's a whole story about how it evolved into its present state. It took 24 years, and thousands of people were involved in this. And, it was an expensive enterprise, but we have to keep in mind that it wasn't just that we were taking that money and, shoveling it into a hole. It was keeping a lot of really good people in good jobs through that period. And here you just see some tiny fraction of the team. This is when it was in the clean room for the second of its tests of the sun shield after the first one failed. And that's part of what the cost was, right? Towards the end of the mission, right before they launched, they were spending tens of millions of dollars a month because they were at their full strength of their team. But when you look at this in context of other things that we spend money on, I don't want to make a statement about what our priorities are as a nation. I put, 4 things down there: the telescope, Social Security, Medicare, and the military. And that's about how much each of us, the average person in the US, spends on each of those things on a per capita basis. And so the Webb telescope cost each of you, and including me, about a buck and a quarter a year for about 20 years. So it cost each of us, a 20. And these other things, I think it's hard to argue that they're not more important to a larger fraction of society. But the fact that we're willing to put just a little bit, an appropriate amount, into scientific exploration is really kind of an amazing thing. And it's something I'm very grateful for because I've been a beneficiary of this, and I feel a responsibility to produce great science because of that. So just going back to this question of a science-based story of our origins. So I think it's really important to frame the kind of work that we do when we're given such a powerful observatory in terms of philosophically important questions. And the ones that I think of most obviously when I imagine what are good uses of this telescope. So things that generally people care about are: where did humans come from? Are we alone in the universe? Is there life elsewhere? And also, what will happen to the Earth after humans are gone? Long after we're extinct. I know we don't like to think about that, but astronomers think in long time scales. So, this is nothing to us. So let me just reframe these in ways that are a little bit more scientifically specific in the way that we approach it for how we use JWST. So instead of saying, where do we come from? One of the main topics I study is when and where did the first stars and galaxies emerge? You can think about this as saying, when did complexity first emerge in the history of the universe? After the Big Bang, when we look at the cosmic background radiation, the universe is smooth to a part in 100,000, and there's no stars, there's no galaxies, there's no nothing. And then at some point, the stars turned on, and then the density contrast between the inside of a star and the space between the stars is enormous. So how do we get to that point, and when did it start? So the question of, are we alone in the universe? That's not really a scientific question, but you can rephrase it and say, can we detect biosignatures in the atmospheres of extrasolar planets? And this is a challenge that JWST can tackle. And then instead of saying what will happen to the Earth after we're gone, we can ask the question, what happens to planets when stars exhaust their nuclear fuel? And there's a textbook answer to this last question that many people will say, all right, the sun will turn into a red giant, and eventually its photosphere will envelop the Earth's orbit, or we'll end our history in some fiery heat death. But there really isn't any, there's no observational evidence for this. That's what the theory tells us will happen. But it's only in the last year, actually, that a postdoc in my group discovered the first example of a planetary engulfment by its host star. And so this has all been speculation until now. But because the photons that were used to discover that all came out in the infrared, you need infrared telescopes to be able to study planetary engulfment events. So these are ways that we use JWST to answer things that I think are philosophically significant questions. And I'm really going to focus this talk on the first of these because that's my specialty. But if you'd like to talk about some of the others during the Q&A, I'm happy to offer a little bit more perspective on those as well. So when I talk about observing things way back in time, it's important to understand that JWST is not only a telescope, but we can think of it as a time machine. And believe it or not, to me, the galaxies that you showed the pictures of at the beginning, they're spectacular to look at. But the ones that we look at with JWST are somewhat more boring to the eye in some ways because they're so far away. And the reason we're interested in faraway objects is that we see them as they were in their past. So to the extent that you have the power to look at faint and distant objects that are way further away than the beautiful pictures you showed at the beginning, you can study it this way. And so I love this cartoon that I saw from, this is actually made by the Japanese television station, did a documentary series about the first stars in the universe. And to explain how this works, if you imagine an observer looking at a child, it's some distance away, that the light from when that child was born takes some finite amount of time to travel to the observer. And if you sort of let this work its way forward, as the light from the infant makes its way to the observer, at the location where the infant was originally born, their time is continuing to march forward. It's just that the evidence of that person's life has not yet arrived at the observer. And so by the time the observer on the right with the binoculars sees the image of the baby, that baby has already aged and turned into an old woman in this particular realization. So this would be somebody who's, at a distance of roughly 80 light years. And the point is that we're always looking into the past by looking further away. And when we're looking back into the early universe, since the universe is about 13.7 billion years old, that would imply that if we're looking in the first billion years after the Big Bang, we're looking at objects that are about 13 billion light years away. And that's sort of a simplified way of thinking about it. That's how long the photons had to travel. But it's a little more complicated because the universe expanded during that time. And so it depends on who's doing the measuring. But let's just say it's 13 billion light years away. And that's about the amount of time that's elapsed. And so we're seeing them for sure as they were 13 billion years ago, not as they are today. Just going back to what I said before, you can think about this in the context of a timeline of the universe. So if t equals 0 is the Big Bang, and the universe is, 13.79 gigayears, that's a billion years today, and our future goes out and to the right. The sun formed when the universe was about 9 billion years old, so it's actually about 2/3 of the way to the present day. The Earth formed almost immediately after, so in the blink of an eye. And microbial life came about 1 billion years after that. And the dinosaurs went extinct 13.7 billion years after the Big Bang. And so most of life as we know it was about 0.09, just a little bit less than 1 billion years on this graph. So up to sort of 800 or 900 million years. So that's not so bad. But most of the time on Earth, at least, life was just these little microbes. So that's a good thing to keep in perspective. And it's in about another, 6 billion years, the sun will burn out and envelop the Earth in our heat death that we described earlier. That's what the theory says. So as I said before, let me not spend too much time on this. We know that larger telescopes are better telescopes, but it's not necessarily just because of their improved diffraction limit. When you're in space, you really do get the benefit of the diffraction limit. But it's also this difference of trying to collect photons. And I think about it this way, like if you want to catch your drinking water, don't stand up and point your mouth upwards. start to harvest it, right? And this is what you need area for. And this is where we actually come to JWST. I haven't really talked about the observatory that much. But this brings us to Christmas morning, actually, on 2021. After all this time, they had to launch it on Christmas. It was actually pretty funny. I and about 50 of my closest friends from work and around the world gathered at 7 a.m. I don't know if any of you from the club watched this in the morning, but it was a pretty amazing event. I was on with the vice president for research of MIT, who was there in her pink bathrobe, which was pretty awesome considering what a boss she is. And we got to see this.
And we have engine start. And liftoff.
Oops. Sorry about that. Let me just bring this back. I was actually trying to answer a question that I thought had come up. So I'll start the video once more.
Okay. Stop. And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
So there it was. So that was my Christmas present on 2021. This launch was an amazing success. It's actually quite remarkable how incredibly perfectly it worked. And it was only the beginning of its journey, but one of the things that was quite amazing about this was that in the process of getting into its final orbit and executing its launch sequence, the precision of the launch was so accurate that they actually didn't need to expend as much fuel as they had originally budgeted to put it into its station-keeping orbit. And that means that they have reserve fuel left to maintain it in its parking orbit. And so that means that the lifetime of the observatory is going to go at least 5 years longer than was originally projected, because left to its own devices, it would actually drift away from its orbital location. So this was an unbelievable triumph technologically, and was just a happy day for all of us. Not only because we had bet almost the whole farm of NASA astrophysics on this mission for the better part of 2 decades, and it was so gratifying to see it come together and eventually work quite successfully. So I did get a question online about the status of the mirrors in a little bit, and I will address that. But let me just explain how the telescope went into its current operational state. So it actually doesn't orbit the Earth in the way that the Hubble Space Telescope does. JWST orbits the Sun at the second Lagrange point, which is, if you imagine that the Sun is here and the Earth is here, then the Lagrange point is immediately opposite the Earth from the Sun. And it's a little gravitational trick where the tug of, when the direction of the tug of gravity from the Earth and the Sun are both pointing in the same direction, it looks like there's just a slightly bigger sun. And that means that you can actually have a spacecraft orbit in a stable configuration with exactly 1 year period, but at a slightly larger distance from the sun. So it's kind of a gravitational trick, but it allows you to be far away from the Earth and all of its thermal and optical light backgrounds. And so it allows you to have a very dark and very cold telescope, which is what's necessary for infrared operation, because JWST is fundamentally an infrared telescope. It's not an optical telescope. So you got to get out to this second Lagrange point. And so this is about 1.5 million kilometers from the Earth. It's called L2. And in the course of that journey, it actually unfolded. So if you look at a little, this diagram that's on the right, this small animation, you can see all the steps. So it was originally folded into this configuration to fit into the launch fairing, also known as the nose cone. And as it went out towards L2, it had to undergo this sort of origami, where first it unfolded the sun shields after putting the solar array out. And then it lifted the observatory mirror off from the instrument package on the back end to give it a little bit of distance. These little flaps are used to provide fine guidance. And then there's this sunshade that rolls out. It's basically like a bunch of layers of aluminum foil. And then these little booms extend out to the right and left to stretch out the sunshade into its proper configuration. And then once that is done is the terrifying operation when they popped open the sunshade, because it has multiple layers, which actually protect the rest of the observatory from the heat of the sun. So there you see it pop open. That's about a week after launch. And that if it was going to fail, that was likely where it was going to fail. Now the secondary mirror folds around from the back. That's 11 days after launch. There's a radiator that helps keep the instrument package cold, and then they rotate the other segments of the mirror into place. And then we just start taking data, except that that's actually not what really happens. Then, so this is 1 month after launch. They do the final burn to get it into the injection. So you have to sort of slow it down like landing an airplane. And that was 1 month into launch. And then there were another 5 months of calibrating the instruments and getting them into their proper operating temperature. You had to wait for it to cool down until the infrared instruments could be turned on. And then you had to align all the mirrors of the primary segments. And that took a long time. So the one thing is that they had to raise up the primary mirror segments from their launch locked positions. So there were little devices that kept the mirrors into a safe vibration configuration. But then after that, they slowly raised them up at a rate of approximately 1 millimeter per day. And the team that was at Goddard Space Flight Center, where they were managing the early operations, actually had a way of monitoring how fast the primary mirror segment was raising up, because they made actually a Chia pet version of a primary mirror for JWST, and they put that on the conference room table, because they've realized that the rate at which the mirrors were going up from JWST was exactly the rate at which grass grows. And so we were all kind of waiting for that to happen. And then there was a quite complex procedure that they used to align each of the primary mirror segments with respect to each other. There was a set of prisms in one of the instruments that they could use to, along with a set of small sub-apertures, and then they would generate interference patterns between the two, between successive pairs of mirror segments. And then they would piston and tilt them in and out until they nulled out the fringes from that slit experiment. And then after about 6 months, it all just worked. It was pretty remarkable. I think it's fair to say that its performance has really exceeded everybody's expectations. And another way of thinking about this is that I think every subgroup of the entire team that built the whole observatory had their requirements that they needed to hit, but they all kind of reserved a little margin because somebody's always going to screw something up, and for something this complicated. But what was kind of amazing with JWST is that all of the subsystems hit their requirements. And so nobody needed to use their reserve. And when that happens, it means that the telescope outperforms what all the projections are going to be for what it ought to do. And really, I've never seen this happen before, and I never expected to again. It really, everything just went right. It was quite amazing. And it was really a joy to watch. So I'm sure there's plenty of questions people have about this. And let me just pause for a second, because there's a Q&A and a chat, which I need to click on something in order to see. So Stephen Schreier asks, what is the present condition of the JWST mirrors and functionality after collisions with dust and meteor particles? That is a very good question. So because the telescope is exposed in outer space, it doesn't have a tube. One of the things that's a big concern is that it is completely exposed. So the telescope is orbiting at 1 orbit around the sun per year. And in the same way that we see meteors when we go, or meteorite trails in the Earth's atmosphere when we intersect regions of the sky where there are comet trails and whatnot, the telescope is going right through those too. And that presents a potentially hazardous situation. And in fact, it was quite alarming, because right after the telescope first started its operations, there was a massive micrometeorite hit that intersected one of the segments. And so people were concerned that all the pre-launch projections were too aggressive and that actually the mirror might degrade faster than people had thought. And in response to that, the NASA has adjusted the operations mode of the telescope to minimize the risk. And the way I was describing it to a few folks before we started the webcast on the call, you can think about it is, if you're driving down the highway and you stick your head out the window and open up your mouth, you're going to swallow some bugs, right? But if you just turn your head around and face the other way and open your mouth, it's going to be okay, right? And you can think about the telescope this way, that we just never want to point JWST in the direction that the orbit is moving. And as long as we avoid that, then the risk of micrometeorite damage goes way down. And so what that's meant is that there's operational constraints on where we can point the telescope, and it's a pain in the neck in terms of scheduling, because there's two conditions that have to be satisfied. One is that the primary mirror there, the gold mirror, has to be on the opposite side of the sun's shield from the sun. So the sort of butt of the instrument always has to be pointed at the sun. Otherwise, bad things happen. And that means that you're sort of limited to pointing towards an annulus that is perpendicular to the sun, but you're also not allowed to point into the direction that the spacecraft is actually moving. And so that's fine. You can still access that point of the sky. You just have to wait 6 months until you're on the other side of the sun and going the other way. And it means that there's a smaller fraction of the year that you can observe certain fractions of the sky when you're near the plane of the sky called the ecliptic, which is the plane at which the solar system's planets orbit. So observing in the ecliptic is a little bit more constrained. If you look out of the ecliptic, you're fine. This telescope's a pain to schedule just in general, but it's worth the effort. So hopefully that answers that question, Steve. I see a couple more things in the chat, so let me deal with those one by one. Do we have any worries about damage to JWST while on station, and has the prior impact had any effect on operations? So I guess I sort of just answered that question, but I will say that the prior impact has not had any effect on performance. It's had an effect on operations because we avoid what's called the meteorite avoidance zone. We just can't point there. But it's a pretty minimal inconvenience because, as I said, we can just point half a year later. And it has not degraded the optical quality of the telescope at all, despite the initial alarm. As far as I'm aware, there's only been one of those events, and it happened right away. And since they adjusted the operations, I haven't heard of another. So Serena Diamond asks, how have the telescope's capabilities surpassed what you expected them to be, and has it had a large impact on astronomy? So what I would say, at least in my own, well, I'm going to talk about how it's affected my own research. But what we found is that it is extraordinarily sensitive to seeing galaxies in the very early universe. And the number of galaxies we've been able to harvest is much larger than we expected by about a factor of between 5 and 10. That's even with optimistic pre-launch predictions. And that's really important because in astronomy, we can't conduct controlled experiments about objects and galaxies because we can't reach out and touch them. That's kind of unique to our discipline. But we can study the physics inside how galaxies and stars form by looking at lots and lots of different objects and then trying to group them by things that look similar. And then that allows us to kind of classify and understand the patterns that go into their creation and evolution. But that only works if you can harvest large numbers of galaxies. And we've just never been able to do that in the early universe. We've really only been able to do that, what I call the local universe, which is, within a few million light years. I call that nearby instead of billions of light years. And when you're looking at the early universe, the gathering samples of those sizes just was impossible before JWST. And now it's basically routine. Like it's actually quite interesting to see how quickly professional astronomers go from being flabbergasted at results to just thinking they're kind of blasé. But that's a separate thing. We say it's blasé, but I think everybody's still entirely excited about this. The other impact that I see on astronomy is that there seem to be quite a large number of measurements of exoplanet atmospheres at this point. And that is something that wasn't really it was sort of available to us before, but not in a serious way, because the systematics and all of the instrumental effects are so minimized when you've got a cryogenic telescope operating at the second Lagrange point in outer space compared to being on the Earth's ground, looking through the atmosphere and under the effect of gravity and thermal loads and the sunlight. And so it's it's had quite a large impact on that field as well. Monica Charmoy, let me just answer one more and then I'll continue with the talk. Monica says, I don't have to answer this right now, but why don't I? Does the ability to detect gravitational waves help JWST circumvent gas in our galaxy that can obstruct its view? Yes and no. So JWST, one of the interesting things is that because JWST operates at infrared wavelengths, it's actually better at penetrating gas and dust than optical telescopes like the Hubble Space Telescope. It's actually quite remarkable that you can, when you have like a fog, infrared photons can see right through it. It's why a lot of military equipment is in the infrared. Besides being night vision, it also is pretty good at penetrating canopy and fog and things like that. But if there's dust and gas in outer space, the infrared can see through that too. And gravitational waves pass through that like nothing happened. So far, we have yet to detect a source in gravitational waves and then followed up with JWST. So right now, most of what we're seeing with gravitational waves are colliding black holes. And by definition, the black holes don't produce any light when they collide. So it's quite interesting and surprising that there's so many black holes that exist. There's another mission that just discovered a random 30 solar mass black hole 500 parsecs away from the Earth, that was yesterday that came out. So there's all these big black holes that nobody ordered that we don't really understand. But I would say it's a dream of everybody to detect not necessarily emerging black holes, but emerging pair of neutron stars, and then point JWST at it and study it. That has yet to happen, but we expect that that'll happen probably in the next 2 to 3 years. So there's a lot of things that have to go right to pull that off. And we're not quite there yet, but it's going to be amazing when it works. So, okay. These are great questions, but I do need to keep it moving. So let me close these guys and continue with a little bit of data. So going back to this picture of the night sky that I showed at the beginning. So let's talk a little bit about context to see how big is the area that JWST can see and how much it lets us zoom in on what we've had in the past. So this is just a photo from that an amateur astronomer took in Australia of a night sky. And I'm going to overlay onto it an image taken from NASA's WISE telescope, which operates at about the same wavelengths as JWST. And now we're going to zoom in so that you can see how much detail there is as you go further and further into detail in the galactic plane. And as you get further into this zoom, you can see that you basically run into the resolution limit of the telescope until I crossfade in the JWST image that you see, so that you can compare the level of detail that you see from these prior NASA missions outside of that region. Actually, let me just pause here. So, oops. So I'm going to pause and so the level of detail that you can see from prior NASA missions is indicated on the outside where you see all these individual stars. And then the additional sharpness that you see from the JWST image is indicated by this overlay, which was actually the first image that was released by JWST. Suffice it to say that it was really astonishing to see how well this worked. And actually, it was quite interesting for me. Like, this is our Slack channel, the first couple of days that data were starting to roll in. And we were starting to look at all the individual frames that came in. And we were I was seeing things in the Slack that I'm not used to seeing among professionals of just people just going crazy over the data that came in. And that was super fun and nice to be a part of that. So let me talk about my program a little bit and the data that were associated with it. I see one more question that came in, but why don't I wait on that? So just to give you a sense of the size of the field of view of JWST for these first data that we took, here's a picture of the full moon. And in August 22, so the telescope was made available for use by the general scientific community in July, late July of 2022. They announced the end of commissioning on July 4th. That was no accident. But then they started releasing actual data a few weeks later. We got ours in early August. And here's about the size of our first image that was taken relative to the full moon. So now you can zoom in and you can see the full level of detail that's associated with this. Now, this particular field that we chose to look at was selected on the basis of the object that's sitting right in the middle. You see a star that looks like it's a little bit more orange or red than the rest of them. That is actually not a star. So all of the other objects with diffraction spikes that you see are stars in the Milky Way. Those are in the foreground. The other little star-looking thing with 6 points in the middle is what's called a quasar. So that's an accreting black hole. And that is coming, the light from that is coming all the way across the history of the universe. So that's at what we call a very high redshift. That's why it looks redder than the other objects. And its light began its journey when the universe was about 700 million years old, so about 7% of its present age. And that was the reason that we chose this field. We wanted to look at that, but we also wanted to look at all those little galaxies that you see. Everything that doesn't have spikes around it in this field is a galaxy. And only the things with the spikes are stars. And it's all those galaxies that are between us and the quasar that are of tremendous interest to us, because using spectroscopy of the quasar, we can study all kinds of detail about intervening matter between us and the quasar. And then we can correlate that with the locations of these galaxies in the foreground that were just not accessible to us, even with the Hubble Space Telescope or other sensitive observatories that predate JWST. And I just mentioned, our group has been planning these observations since 2015. Like, that's when we knew we were going to get the time. But we were just patiently waiting for the first photons to come through. You know, after many launch delays, you can't believe how happy I was when this came in and we saw how good the data were. So just zooming in around the galaxy, again, so the quasar is now just shown in a blow up in the middle. And although there's some pretty cool pictures of galaxies that are nearby, these are quite small, like this ring-shaped galaxy that you see over to the right. That's probably only an arcsecond across. But because you have a 6.5 meter diffraction limited telescope in space, you can resolve it, right? That each individual pixel is 0.03 arcseconds across, and it's barely sampled. But the objects that we're interested in looking at, if you want to look at things that are all the way across the universe, they look like the faintest, most boring smudges that are just these tiny little dots that you see around the location of the quasar that are kind of nestled among its diffraction spikes. Like those redder objects that you see inside the diffraction spikes at maybe like 11 o'clock or so. You see 2 red objects. Those are the kind of things that we're studying. And so it's not that we're taking, you know, at least people who are doing professional scientific observations are not just taking pretty pictures of gigantic galaxies. We're looking for these faint things that are not that spectacular in JWST images, but they were just completely impossible to observe with anything else. So again, there's the quasar. So these are 3 galaxies that are at the epochs that we're interested in looking at. These are these sort of first galaxy objects. They look boring, but we love them just the same. They're by far the most interesting objects in this image, to me at least. So just to give you a question, like you might say, oh, those don't look like they're very high signal to noise. So here they are in JWST, and I've just shown them in a single color image, one where white corresponds to brighter objects and black colors correspond to the sky background. I've stretched the image hard, so the sky doesn't really look black, but it gives you a sense of where the noise level is. Now I'm going to flash an image of this same field taken with the Hubble Space Telescope so you can compare and contrast the performance. So that's what this looks like to the Hubble Space Telescope. And here's the same field in JWST. So I'll just flash them back and forth so you can compare individual objects and see. I haven't registered them completely perfectly to each other, but I think you kind of get the point, right? It's a whole new ball game. And if you look particularly at these sources that I've circled, you can see they're just not there in the Hubble images. It's just not sensitive enough to see them, even close. And it's just that there's no question with JWST. It's like shooting fish in a barrel, right? For these things, it's pretty amazing, and it was just jaw dropping when we first saw these things come in. So these are what pictures look like. So here we are, back on that same image that I showed before. And as I said, the quasar is sitting behind all the other objects. But I want to we were predicting that we would see something like 10 or 15 of these very high redshift galaxies from the early universe, based on prior modeling and the projected sensitivity of the telescope. So I'm going to circle and highlight all the objects that we saw in our first field that were from that same epoch that we were interested in. And that was what we saw in the first go around. The redshift that you see down there is basically a measure of distance. So a redshift of 6 corresponds to when the universe was about, I would say 8% of its present age. And so all of these objects are color-coded by their actual distance, which we can measure, and I'll show you how we measure that in a little bit. But the point is, this surpassed our wildest expectations for how well we thought this telescope was going to do. And every field that we've studied since then, it was not a particular aspect of this field. This is what we see everywhere. So part of this it's a sort of a conspiracy of both the universe producing really bright emission lines that we could use to measure the redshifts of these objects, but also the telescope just performing at a bonkers level that allowed us to measure all of these things. So it's quite exciting. When we first saw this, we knew it was a bonanza. So let me show you a couple examples of these things. Let's zoom in on them. So I've cut out some postage stamps from that image. So at the bottom, you see, just going back to that timeline, the epoch that we're talking about when these galaxies were made. So this is the sort of bracket of range for this 4x3 object matrix. So these objects, they look kind of red. As I said, that's because the universe is expanding away from us. And these objects are very, very, very distant. Edwin Hubble's law says that things that are further away from us are expanding faster. Things that are expanding away from us faster, we see it looking redder because of the Doppler shift. And so these things, what would normally be seen at ultraviolet wavelengths, are seen way into the infrared. This is like 3 microns. And, it's 10 times, well, it's about 7.5 times stretched in wavelength. So this is what they look like. They're not too spectacular. Some of them are interesting. You see evidence that some of these things are merging. There's some double objects. But by and large, they just look like kind of dots. But they're still quite compact. And as I said, those pixels are only 0.03 arc seconds across. So they're much, much smaller than the Milky Way. So let me just give you a little bit of context for how big these are relative to the Milky Way. So this is not an image of the Milky Way, but it's an image of a galaxy that's kind of Milky Way-like. So the Milky Way has about 70 billion stars, and it's forming about 1 new one per year. And it's about 90,000 light years across. And if you go into the southern hemisphere, those of you who have been lucky enough to do that, will probably have seen the Magellanic Clouds. So those are 2 dwarf galaxies. There's a big one and a little one. And they're on an orbit that's going to cause them to merge with the Milky Way in the future. And in this diagram, I've shown them at approximately their appropriate relative size and distance from the Milky Way. So this is all kind of shown roughly to scale. So I've pointed out the small Magellanic Cloud that has only about a little less than 1% of the number of stars that the Milky Way does. And it has a few percent times the Milky Way star formation. So it's forming stars relative to its size a little bit faster than the Milky Way, but not by that much. But we would call it a starburst galaxy because its star formation rate relative to its size is elevated. So now let me show roughly to scale the size of these baby galaxies that we're seeing in the early universe. So this is that same set of postage stamps. And what you see, so I've made them the same rough linear size as the Milky Way and the Magellanic Clouds here. And you can see that the range of these galaxies is sort of similar to the small Magellanic Clouds. So the SMC is short for small Magellanic Clouds. Some of these galaxies are a little smaller than the SMC. Some of them are a little bigger. Nothing's as big as the large Magellanic Cloud. And certainly nothing is nearly as big as the Milky Way. It's like a fraction of the size of the Milky Way. And it's more like the size of one of those star clusters that you see in the Milky Way. And so, they're only about 1% the size of the Milky Way in terms of their stars. So there's about 10 million stars in a typical galaxy like this, maybe 100 million tops instead of 70 billion. But they're forming stars at an extraordinarily high rate. So they're forming stars at roughly equal to the rate of the Milky Way, or maybe a factor of 10 more vigorously than the current Milky Way. So what it means is these things are tiny, but they're growing really fast. Again, it's like an embryo, right? That's doubling in size really quickly. And it's not a fully grown thing yet. And so I just find it still kind of remarkable that James Webb is capable of seeing the Small Magellanic Cloud at a distance of 13 billion light years. Right? That's a pretty amazing telescope that can do that, and that allows us to study these things when they are at their early stages of evolution. I mentioned that I would talk about how we discover the distance to these things or measure the distance, and that's using spectroscopy. And so let me explain what that is briefly for those who aren't familiar. Some will be. But a way of thinking about it is that often it's said that a picture is worth 1,000 words, but I always say a spectrum is worth 1,000 pictures in this case, because a spectrum is made by putting a prism or diffraction grating or some other dispersive element in front of or in the optical path of the telescope so that it creates a little rainbow on your detector. And then this allows you to measure all kinds of things in more detail. So you can measure the distance to an object or something about its chemistry or its radiation field. And so here what I've shown is if you were to put a prism in front of the focal plane of JWST, it would turn each of these galaxies that you see in the sort of cross-faded image into a little rainbow. This is just a simulation of what you would see, but it's basically the same idea. And then by measuring the intensity of light at each one of those colors in the rainbow, we can use that to determine all these things about distance and chemistry and what kind of stars are producing its light, or if there are nebulae in it. And in fact, really what we're usually doing to measure the distance to each object is looking at the nebulae in these things. It's like looking at the Orion Nebula all the way across the universe. If you look at Orion with an H-alpha filter, we can do that just at 10 billion light years. And we're looking at an H-alpha, or for most of the, if any of you have taken pictures of nebula with oxygen-3 filters, most of what we're doing with JWST is measuring redshifts using oxygen-3, except that we're observing oxygen-3 at a wavelength of like 3.5 microns instead of 5,007 angstroms. And that's because of the redshift effect. And so you need an infrared telescope to do that. I know that's a little bit inside baseball, but for those of you who have observed with oxygen-3 filters, you'll know what I'm talking about. So when you take a spectrum, you can plot a measure of the intensity versus wavelength. And this is actually an example of an object at redshift 6.76, which was like, I have never observed an object at 6.76, at least at stars and gas and nebulae until JWST. And now look at the signal to noise of that spectrum. It's crazy good. And there's the object. And so it's the pattern of those oxygen lines plus H beta and hydrogen gamma and delta that allows us to measure the distance to the object with extraordinary accuracy. And so James Webb allows us to do that. This is actually what the data look like coming straight off the telescope. So it doesn't look as beautiful as that other one. You see all kinds of bad pixels in here, and we get sort of monocolor images. You see all these things, these artifacts that look like, we call them snowballs, and like the data processing has to deal with all of those. But after all of the processing happens, you can actually measure distances to all of these objects. And the reason this is so interesting, and I'll just stop the share here for a second. I put this particular slide in to remind myself to show another thing here. So this is just an interactive figure that shows what you get when you measure redshifts. So this is actually a view of all of the galaxies in our field. So if you look at in right ascension and declination on the sky, and the bore side of the telescope is at this red dot here, and then all of these green dots are the locations of galaxies we detected. when we measure these spectra, we figure out the distances to all of the objects. And it allows us to actually rotate this out so you can see in a three-dimensional space now, instead of just in 2 dimensions. So let me zoom out a little bit. What you can see is that there are superpositions of different clusters of galaxies, but now this sort of depth dimension is along the line of sight, which is something that's not available to you in a normal image. And here, the black hole quasar that you see is shown with the yellow dot. And you can see we discovered a big cluster of galaxies around this object, and we've used that to measure the mass of the galaxy and its black hole. But then you also see all these things in the foreground that are quite interesting, and studying that clustering is pretty cool. And so it allows us to take this, original, what amounts to a 2D image like this, that you would get if you just took a picture of the sky. And now we're able to study it and rotate it out in this way, which is something that wasn't possible before. Let's see, I'm going to go back to the presentation. There was a question from Monica Charmoy that says, what insight can JWST provide on the CMB? And the answer is not much, right? The CMB is observed with different telescopes, but JWST allows us to connect the dots between what we see today and what we saw in the cosmic background. So it's sort of like, oops, let me share this before I go full screen. So it allows us to get a different epoch. So before, we would start our cosmological simulations after the cosmic background, and then just compare that to the present day. But allowing the ability to see another epoch and measure it in detail early in the universe, basically is a way of, again, I said we can't control experiments because we can't follow the time evolution of an astronomical object in human life scales or lifespan. But if we can observe at many different epochs in the history of the universe, then we can kind of thread that together and create a physical simulation that matches observations at each epoch that we can observe. And JWST gives us an epoch that's closer than we've ever been before to the cosmic background. So just moving through, I would say the early science findings that we've had, the first, as I've said, well, this is actually more than 5 months in now, but I think the results haven't changed that much. There's sort of a conspiracy of physical parameters plus a good telescope means that we're finding way more objects than we expected. These objects are really small and they're tiny, and they're forming stars at a prodigious rate. And there is a lot of evidence that these early stars were making heavy elements and filling out the various elements of the periodic table. And there's also evidence that we're starting to see radiation from these early galaxies interacting with the surrounding gas of the intergalactic medium, meaning that we've reached the epoch when the stars are first turning on. So this is all stuff that's happening. It's kind of amazing. And this is kind of where JWST is taking us right now. So, a question you might have, and I'll sort of finish up with this, not too much on it, but how is it that we actually end up getting time on this telescope? Like, this is a pretty amazing thing that happened, and it was probably the highlight of my career, at least. And I think there's a whole interesting story about how professionals work and are able to leverage these different resources. So in our case, it involved a lot of preparation with the Magellan telescopes. As was said in the beginning, I've spent a lot of time observing at Magellan. This is at Las Campanas Observatory in Chile. This is a photo taken by Yuri Beletsky during a lunar eclipse. There you can see the Magellanic Clouds on the left, and the moon on the right, and then the Milky Way, and then the lights of La Sirena on the horizon. It's a quite dark sight compared to anything you'd see in North America. These are two 6.5 meter diameter telescopes, and I do most of my research there. MIT owns a 10% share in these telescopes, and I build toys to put on the back end of these telescopes. So I didn't build these telescopes myself, but I work on things that go on the business end. So this is an example of the kind of thing that we build. So there's me with a hard hat on the right for scale. So this is my lab. So this is a cryogenic infrared spectrometer I built for the Magellans. Here you see us lifting it onto the telescope, and then also the inside of the vacuum chamber that we were working on at the time we built this. this was basically my tenure package at MIT. So getting this thing on the sky and getting it to observe these objects was what I built my case around. And this instrument actually discovered a lot of these quasars in the early universe, which were the things that we eventually pointed JWST at. And because we had a lot of spectra that were taken with this instrument on the ground a decade before JWST flew, I was not working directly on JW, but there were other people who were involved in the construction of and advising NASA on scientific decisions for how to build and configure the telescope, that being James Webb. And they, in exchange for that time, that they spent advising NASA and sitting in endless committee meetings, they were given a guaranteed allocation of time in the first cycle of proposals. And one of those PIs approached me and said, we heard that you have this data from Magellan. We're interested in pointing JWST towards this. Could we collaborate on a project where you give us your data from Magellan, and then we'll work on JWST. And through that, we were able to spend 100 hours on JWST in its first cycle. And so we've completed that. We were observing 5 different fields. So it was 20 hours apiece on each of these fields with JWST. I'll note that at 6.5 meters, the telescope you see on the right, Magellan, is the same size as JWST. It's just that one of them's at L2 and one of them's on the ground. So there's a different set of challenges for those two. This is a bit about let me skip this part about the sort of sociology of scientific collaborations, but the point being, we were scattered all over the world and did a lot of this work on Zoom because it was during the pandemic. It was quite something, but we made it work. I do want to mention that in the same way that telescopes like Magellan really complemented the Hubble Space Telescope, there's going to be a new generation of telescopes built in the next decade that will pair with JWST. And I think they're going to be around for 50 years or so. And these are things that are going to be 25 to 30 meters in diameter. And they cannot be made out of single mirrors the way Magellan is. But if you look on the right panel here, you see the Magellan telescope. This is the one I was standing next to. And you can see a human for scale standing under GMT, which stands for the Giant Magellan Telescope. So this is going to be a single telescope that's composed of 7 8.5 meter diameter off-axis segments. And that's going to be built on the same mountain as Magellan. So on the left, you see the site excavation. Magellan telescopes are the 2 little dots that you see over on the far horizon. And then in the foreground, you see the excavation that's happening to pour the foundations for the Giant Magellan Telescope. And so, the quest continues. We're going to be doing the next generation of things as close to fruition, and it's on its way. There's a lot that has to happen before those telescopes are done, but I think it's going to be a big part of the scientific endeavor for astronomy over the next decade is to bring these telescopes into existence. And I'm really excited about this. This is just one of the 7 segments that's been cast at the University of Arizona's rotating furnace. And it's really going to be a kind of an awesome opportunity for technical innovation. Hopefully, it would be a delight for me if my career is long enough to see both JWST and these telescopes come into being. I think it's likely to happen, but we'll see. But these are well underway now. And there you see just a layout of an instrument that my team is working on over on the right. But let me not get into the details of what that looks like. I think that's kind of the end of what I had prepared. I'll take a few minutes to answer questions and stuff, but I just wanted to sort of circle back to this question of origin stories, right? So this is actually a picture taken at Stellafane by one of the colleagues in my group. Who knows, this might have been one of your telescopes for all I know. Those of you who have been to Stellafane probably have looked through this telescope. It's a famous one.
It is our telescope.
Oh, it is your telescope? Awesome. All right. I'll get Gabor in touch with you guys.
We have that image.
Oh, you have this one?
Yeah, we use it all the time.
Oh, okay. Oh, okay. Did you get it? Well, we can talk about that later. I've always loved this one just because it sort of gets me back to why we do this. And telescopes should be a way for us to understand what's out there. And I think it's important for me to try to connect it to these kind of questions that are important to humanity, right? And the way that I approach that, besides, the playing with telescopes and gadgets is like, that's for me, that's my own fun. That's just what I like to do. But the question of like, where do we come from? Where are we going? How does this all play into the human story? I think those are important to everybody, or at least they should be. And it's to us to try and make people understand the importance of those. And that's something that's like kind of separates humans from other animals on our planet, that we're interested in those questions. And I think it's quite fortunate that we have an observatory that's capable of really kind of taking on those questions and tackling them. And it makes me want to get up every day and do my job, right? People always ask what it's like to be a professional astronomer. Do you get to think about these things every day? Most of the time, we're just on Zoom or writing email. But every once in a while, you get to do one of these things that like reminds you why you took this job, right? And this sort of early period of JWST has been one of those moments. And so, here's a picture of it. This is the last view we got to see of JWST before it went off to L2. And so I think we're just super lucky to be at this moment in history when we can have this amazing observatory, and that's been supported by all of our taxpayer dollars in order to do something it's like just a huge go big or go home experiment, and it worked, and it's working, and it's going to work for a long time, longer than we even could have predicted. So it's quite a pleasure and an honor to get to use this thing, and it's been super fun, and I love getting to share it with all of you. So so that's what I had to say. Let me stop and see. I see there's 3 things that are appearing in the Q&A. So why don't I address those, and then we can take other questions from those of you who are on the panel as well. So I'm going to stop so that I don't somehow freeze my screen again. So I apologize for that earlier. So let me go to the Q&A first. Oh, actually, so I see, did grad students or undergrad students participate in your JWST research at MIT? The answer is yes, to all of the above. I would say more graduate students than undergrads. I talk about how wonderful this was, but it's also incredibly competitive in a way. And there was, especially in the early phases before lots of groups had data, there was a lot of pressure to get the early results published very promptly. And I was reluctant to put undergraduates in the critical path of that so that they could feel the sort of the white heat of that. But now that we're kind of a year and a half, 2 years into operations, we're involving everybody in this kind of research. And the graduate students are leading a lot of the way for this, using ideas that come from their supervisors and advisors. But I think there's a place for everybody in this. So I think the short answer to that question is yes. I see 2 other questions. Has JWST made, so from Stephen Schreier, has JWST made any observations or discoveries about the center of the Milky Way, Sagittarius A? I don't know the answer to that question. That's a very good one. I only assume that they're spending some time pointing in that direction. I'm a little worried that things might be too bright towards Sag A. On the other hand, they've observed Jupiter, so it's probably okay. I would say that people have been able to use adaptive optics with telescopes on the ground to study the galactic center very effectively, and also using millimeter and radio telescopes. There's this famous picture of the black hole in Sag A star produced by the Event Horizon telescope. That's also pretty spectacular. But to the extent that JWST has observed Sag A, I don't know that it has, either they haven't published things or it hasn't really penetrated the zeitgeist for those of us who are outside the galactic center field. But that's a really interesting question. I'm sure somebody has pointed in that direction. I just don't know. And then the second question is AI being used to analyze the vast amount of data that JWST collects? Yes and no. Astronomers have lots of opinions about AI and what it should and should not be used for. So I will say, people are using AI to analyze our data constantly. I mean, it's just like a part of the toolkit now to a certain extent. But there's a little bit of reservation in that one of the aspects of AI that is kind of baked in is that oftentimes it produces an answer that is compelling or interesting or even right. But it's often the case that you don't understand why or how it produced that result. And as physicists, we're really interested in the why and how. And so we use it to guide our intuition, but then usually we try to follow that up with some sort of underlying theory. We try to use that to narrow down the theory space that we can use to try and explain what's going on. But we tend to be a little bit distrustful of results that we don't actually have an explanation for, because the explanation is the thing for us. Like that's the end. But it's also true that there's a lot of stuff that we don't care so much about, which is like the details of how the data are processed from their raw form into the final form, and like how you calibrate the wavelength solution of the observatory or things like that. We care about those. Well, it's not fair to say we don't care about them, but that's just a means to the end. And people do use AI to try and understand their instruments and calibrate them, and to regress out a lot of the instrumental features that appear in your data, so that we can get at the heart of the scientific interpretation. And so there is an overall sense that using AI to deal with your data, especially when there's very large volumes of it, is fair game. But there's a pretty interesting debate that's going on in the scientific community about like, when is it and is it not appropriate to use AI? If you're talking about business or other things like that, all you care about is that you got an answer that's right. And like, you don't necessarily care that how you got there. Like, as long as it produces the predictions or information you want, that's good enough. But we're just kind of in a different business. And so it's a little bit unique. But I think that the answer to that question, ask me in 6 months, I might have a different answer to that question, Stephen. It's a really interesting one. So I think those are all the questions that I have online. Any other things? Yeah, sure.
It's kind of an oddball, but you mentioned earlier that you have spectra from the Magellan telescope for some of these distant quasars or galaxies.
Just the quasars, not the galaxies.
So quasars, so much the better. And presumably James Webb's going to work for another, I don't know, 10, 20 years, whatever the fuel is left on that. And then you'll have other telescopes coming online, like Giant Magellan and so forth.
Yep.
Do you think that over the course of decades, might take 100 years or so, you could use that spectra to directly resolve the Hubble tension?
Yes and no. So it is the case that if you are able to take spectra of a large number of objects at one epoch, and then you go back many years later and observe them all again, all of their redshifts will have changed a little bit because of the overall cosmic acceleration. Whether that removes the Hubble tension, I'd have to think about that. So there's always this concern that we're living in a slight overdensity or underdensity that's expanding slightly faster or slightly slower than the rest of the universe. And I think that the redshift drift effect that you get is quite sensitive to your locality. So you'd be able to measure with very high precision what the expansion rate is. But it's quite sensitive to the last bit of the travel of those photons from the distant object to us. I'm not sure that JWST you need very high spectral resolution to do that, and the JWST does not have that. But the extremely large telescopes are going to build instruments that do. And in fact, that's part of the science case for these new generation of ground-based telescopes, is to measure this. It presumes that your telescope is going to be around for about 50 years. But you have to observe many objects, because when you see a slight redshift drift, There's a lot of things that could cause that. Most notably, anything that moves inside of the galaxy, right? And things are moving inside the galaxies all the time. And so you have to observe so many galaxies that it averages out all those motions. And then only in the aggregate, you can start to see that.
Right.
So-
I'm just thinking it would be a direct measurement rather than inferring it from something else like cosmic microwave background.
Yep. Yeah, this is called the Sandage Lobe effect. This was we did a problem set on this when I was a graduate student. Actually, it's an excellent problem for a first year graduate student. And so yeah, you get an absolute direct measurement. But it's, you need to measure the redshift to a part in 10 to the 6. And that's hard to do. Yeah.
I guess you have solved all the mysteries of the universe.
There it is. I really appreciate the invitation to come here. This is really
Thank you for the wonderful presentation, and we learned a lot. Thank you very much.
That was great. Thank you.
Yes, thank
Right.
you.
Thank
So,
you.
have you back
Take care,
again.
everybody.
Thank you.
Have a good night.